Welcome to week two. So in week one, we talked a lot about where do the electrons kind of live? Like how do we represent electrons when we draw organic structures, and how does that mean? What does that mean, right? And so we talked about things like sigma bonds, pi bonds, lone pairs, and carbocations. Those are the four main elements of every organic structure. And so what we're going to talk about today is we're going to talk about what happens when those electrons start to move. How are we allowed to move them around? And all that kind of stuff. And we're going to start simple. We're going to start with just a molecule on its own without anything else reacting with it or anything like that. And we're going to talk about resonance structures. Okay, so resonance structures are going to be the movement of electrons within a molecule. We're going to talk about what we're allowed to do, how we're allowed to move them, and also what makes a good resonance structure. Which way do we want to move them in order to make our compounds more stable? Because as always with the movement of electrons, the goal is to make something that's more stable. Okay, so let's switch this over. I will see if I can get this thing to start writing. I cannot. We're close now. All right, resonance structures. Resonance structures in organic, right, are all about the movement of electrons. And so we're kind of asking two questions. Where do electrons start? So if I give you a structure and I ask you to draw a resonance structure, you need to be able to identify which electrons am I allowed to move. Right? And this is a pretty quick answer actually. Of the places that we've talked about where electrons are, there's only two possibilities. So the electrons that you're going to move are always going to start in either lone pairs or pi bonds. So when you look at a resonance structure, you're going to look for where are the lone pairs, right? We need to identify where are the lone pairs, and we need to identify where are the pi bonds. And so a lot of the exercises that we've been doing, looking at, degrees of unsaturation, looking at formal charge and lone pairs on heteroatoms and that kind of thing, that's why this is important, because we're going to use this. All right. And then, of course, the second, if we know where the electrons start, we also want to know where are they going. Where are electrons going, right? And the answer is that they will always form new lone pairs or new pi bonds. And so really, resonance structures boil down to lone pairs and pi bonds making new lone pairs and pi bonds. Okay? So there's a couple of things that uh, kind of enter into this. One, you'll notice that sigma bonds don't have any role in resonance, right? So if you're moving sigma bonds around, if you're breaking sigma bonds or moving electrons out of sigma bonds or making new sigma bonds, you're not doing resonance. That's something completely different, and we're definitely going to talk about that, but it's certainly not what we're doing right now. So let's see here. Well, I got to write this down. I lost my penning, and there it is. So this is an important rule. Cannot make or break sigma bonds in resonance. And so because it's organic chemistry, let's put that in the context of carbon, right? Carbon is that's our thing that we're mainly talking about. And if we can't make or break sigma bonds in resonance, then that means that any sp3 carbon, and go back to hybridization, we remember that sp3 carbons are carbons that only have sigma bonds attached to them. And any sp3 carbon that's neutral cannot participate in resonance. Right, so if we have, let's draw an organic structure like this, right, and we have these pi bonds here and here, right? These pi bonds, we might want to think about moving them around if we were doing resonance, but because there's a neutral sp3 carbon in between them, neutral, sp3 carbon. That means that we can't move electrons through this position because this carbon has sigma bond, carbon-carbon sigma bond, carbon-carbon sigma bond, carbon-hydrogen, carbon-hydrogen, right? When we have a neutral sp3 carbon like this, that means that we cannot use that carbon in resonance. And so that means that we only have these electrons over here can only end up with one of these two carbons on the end or over here, and same thing over here. These electrons can only end up there or there. Okay? So there's only 3 allowed moves in resonance. 3 allowed moves. The first one is you can take a lone pi bond and make a lone pair. So if you start with a pi bond, let's do you can break that pi bond and move those electrons to make a lone pair, right? This oxygen already has 2 lone pairs, but when we draw resonance, we can get an additional lone pair. And we recognize that when oxygen has 3 lone pairs, that means that it's negative, right? And this carbon down here now only has 3 sigma bonds, and it lost its electrons, so we've made a carbocation as well. But this is a resonance structure where we've taken a pi bond, we've moved these electrons that were in the pi bond up here to make a lone pair. The second allowed move is we can take a pi bond and make another pi bond, just in a different place, right? So this is usually what happens with carbocations. So if we have a pi bond and we have a carbocation next to it, right, we can take these electrons and make a new pi bond that's over here. Right? And we've moved that carbocation, or the carbocation has ended, like this carbon on the end has created a carbocation because it lost electrons. But when we move this pi bond over, we're creating a new pi bond over here. Right? Notice that the carbocation's not moving. I don't want you to think that this plus sign ever moves, right? Because plus sign, the carbocations are not one of the things that we can move around in resonance structures. What we're doing is we are satisfying this carbocation, we're making this carbocation neutral, and we're creating a new carbocation over here, right? These two carbocations are not related to each other. One didn't come from the other or anything like that. The third allowed move is we can start with a lone pair, and we can make a pi bond. And this is, of course, just the reverse of the first move, right? So you can imagine if we started with something like this, we could take these electrons, move them down to make a pi bond. So let me think about this. How do I want to draw this? Yeah, we'll just draw the reverse of that. Right, we can take one of these lone pairs and we can move them down to make a pi bond. So these are the allowed moves of resonance. Take a pi bond, make a lone pair, take a pi bond and make a different pi bond, or take a lone pair and make a pi bond. If we know these rules, if we follow these rules, we're a long way towards making good resonance structures. The last thing I'm going to say in this video is this is one of those rules that is easy to forget about, and then you'll get it wrong, and then you'll look back and say, oh, I knew that though, right? So this rule is we can only move electrons to neighboring carbons. Oh, not neighboring carbons, neighboring atoms. They don't have to be carbons. I'm an organic chemist, but I'm not going to require that everything be carbons. Right. So notice here, right, I took this pi bond and I moved those electrons, but they were connecting the C and the carbon and the oxygen. Those electrons moved to the oxygen. I can't take them and move them to this carbon over here that doesn't have anything to do with this pi bond, right? Same thing here. When I take this pi bond, I move it one position over to share with a carbon that's connected to the carbons that are part of the pi bond, right? I can't move this like across a molecule. So if I had something like this, where the carbocation's way over here, I can't move these electrons to that carbocation. That's not going to be resonance, because again, notice what we have in between, right? We have these neutral sp3 carbons. And when we have neutral sp3 carbons, they cannot participate in the resonance. And so we can't move the electrons through those because that would involve breaking sigma bonds or making sigma bonds, and we can't do that in resonance, right? So we can only move to neighboring atoms. All right, I think that's enough for this video. There will be another resonance video coming shortly, so where I'll just talk a little bit more about the rules, talk a little bit about resonance stability and all that kind of stuff. So look for that one next, and let me know if you have any questions. Thanks.